All right, so we were doing multivariable functions, and the two types of applications we're going to look at are marginal analysis, which we did at the end of 6.2, and now optimization. And there's two types of optimization that we're going to look at. The first type is the relative extrema case, with a function of two variables. And so the MyLab does a pretty good job, and they were able to pop up three-dimensional pictures here. But basically, the relative extrema definition is exactly the same as the one variable case. The difference here is, though, you have to have two variables, all right? And so that makes it a little more complex, but it's basically the same idea. You get a relative maximum at a point, and again, now it's a point, an x and a y value, an a and a b. A is your x, b is your y. If it's in the domain, so again, it has to be in the domain of the function. And most of our functions are ones where the domain is either all reals or the positive numbers. If that point is bigger than or equal to all the other points on my function f of x, y. Same thing in the minimum case. All right, minimum if the point CD, which is, again, C is the x value, D is the y value, if it's f of CD is smaller than or equal to every single value. And again, the circular disk has to do with the fact that it's relative, meaning there might be a bigger or a smaller value someplace else, but as long as it's kind of in like a peak or a valley spot, that's the kind of isolated, so it's relative. Absolutes are found using the previous definitions where it's on the entire domain, all right, not just near the point. So again, it's just like the one variable case. All right, so functions, whether they're one variable or two variables, can only have relative extrema or absolute extrema values in the domain. So in this case, there's just two values that have to be in the domain. X has to be in the domain and the y has to be in the domain. All right, so that's the first thing, has to be in the domain of our function. All right, and then the second thing, it has to be a critical value, just like the one variable case. Critical values give us our possible relative max, relative mins, or absolute max, absolute mins. All right, so the first thing we do is we have to find the critical values. Now, again, because it's a multivariable function, critical values are a little harder. There's a little more algebra involved. All right, the critical point of a function with two variables, like the one variable function, can only occur at values in the domain. And the difference here is there are two directions that have to be stopped, right? I have an x direction and a y direction. And both of those directions, the rate of change has to be 0. There are cases where the rate of change is 0 in one direction and not 0 in the other direction. That would not be a critical value. Critical values are when I'm 0, right? My rate of change is 0 when I move in the x direction, and my rate of change is 0 when I move in the y direction. And so you have to find a system of equations where the first order derivatives are both 0 at the same point. All right, so again, that's what that means. A critical point, some x value a, some y value b, in our function xy, if and only if both at the same time, both the first order derivative with respect to x and the first order derivative with respect to y are stopping points, are zeros. All right, so it's not moving in the x direction at that point, and it's not moving in the y direction at that point. It's constant at both moments. And so what you have to do is, well, you have to solve a system of equations with two variables and two unknowns. All right, so you find your first order derivatives, set them equal to 0, and solve. There are two methods, as technically there are three, but the third method really isn't a system, and I'll explain when I get there. All right, so the methods if I have a system. So I've got a function of x and y set equal to 0. I've got a function of x and y set equal to 0. All right, we have to solve the system where we've set them equal to 0. All right, the first method is the substitution, and it works in every single case. All right, the substitution. You pick one equation, solve for one of the variables. So you pick equation 1, solve for x. Or pick equation 2 and solve for x. Or solve for y. All right, so there's multiple ways you can do it. Usually there's an easier way. You know, one variable is a little easier to solve for and substitute out than the other, but not always. All right, so you pick one equation, solve for a variable, you substitute that into the other equation, which should give you a single expression with only either x values to solve for or y value to solve for. All right, and then once you figure out whatever the x value is or the y value is, you have to do a substitute back into one of the original equations. Excuse me. To find the missing point, all right, because I needed both an x value and a y value. All right, the second method is a special case, which allows us to use technology, use our graphing calculators to solve. So method 2 only works. I can use matrices, which I can use, and I'll show you how to do this when we get to it. If they're linear, meaning you can use a matrix to solve your system of equations if your first order derivatives are linear functions. Linear functions mean I can write it in the form a single x term plus a single y term set equal to a single constant term. Right? There are no squares, cubes, mixed variables. All right, so that's what it means to be linear. And again, you have to put it in that form in order to use the matrix. X value first, y value second, set equal to your constant value. Right? Then you plug in your system in your calculator and it solves it for you. It does the algebra for you. It does the row reduced echelon form. All right, those are the two methods if we have a system of linear equations where my equations have both x and y values in them. The last little note here is if I don't have a system. All right, and this will happen, actually, my first example will be this actually note case. If your first order partial derivatives are only in terms of one variable. So I find my first order derivative with respect to x and there's only x values. And I find my first order derivative with respect to y and there's only y values. Well, I just take the equation that just has x values, solve for x. Take the equation that just has the y value, solve for y. And so that's not a system in that case. It's just a single expression I can find for x and a single expression I can solve for y. All right, and actually my first example is going to be sort of that special case where it's not a system, I just solve for my variables in the individual equations that they're given. All right, so that's the process, and then we'll go to practice it in the next videos.